Okay, so today we're looking at section 6.3. Section 6.3 is about confidence intervals for population proportions. So much of what we do in statistics is centered on the concepts of probability. When we compute empirical probabilities, we use this formula. So you may remember this back from when we were first introducing probability in section 3.1. Probability is equal to the number of successful attempts divided by the total number of attempts. So when you think about what this fraction is, it's actually a population proportion, right? It's some portion of the population of attempts, how many were successful, divided by the total number. That's how we make a proportion. And so a probability P is really just a population proportion. Okay, so we're going to use the techniques similar to those in the previous sections to create confidence intervals. So just like in 6.1 and 6.2, where we found various ways to find confidence intervals for the mean, we also want to be able to use confidence intervals for population proportions. So we have to get a point estimate. Remember when we were doing the confidence interval for the mean, the point estimate was the sample mean. So what would our point estimate be for a population proportion P? Let's look at the point estimate for P. For the point estimate for P, we're going to call that P with a circumflex over the top. That's what that little angular thing is called. It's a circumflex. And the way we define it is that value is equal to x over n, where x is the number of successes in the sample, and n is the sample size. If that is the number of successes, the population proportion for the number of successes, then the population proportion for the total number of failures will be q with that little circumflex over the top. And similar rules to what we've seen before apply. We've talked about p and q, right? Well, if you see the q with the little circumflex, that's going to be 1 minus p with a little circumflex. We've seen that the probability of success plus the probability of failure should add up to 1 because those are complements of one another. And so we're not going to call it p with the circumflex or q with the circumflex. What we call them is p hat and q hat because it looks like the p and the q are actually wearing little hats. We're going to have to come up with a margin of error formula. We had a margin of error formula when we discussed the mean. Now we need a margin of error formula to discuss population proportions P. Here's our margin of error formula. So when we're estimating the true population proportion P with the value P hat, the margin of error E is given by this formula, ZC times the square root of P hat Q hat over N. So a little bit different, but not really from the margin of error that we used when we were discussing the mean. And we'll see why here shortly that it's not really all that different at all. So when we were dealing with the sampling distribution of sample means, we had this statement, n times p and n times q had to be greater than or equal to 5. Well, in this context, n times p hat and n times q hat both have to be greater than or equal to 5. And the result here is that our mu of p hat is going to equal p. So just like we had mu of x bar was equal to mu, which was the population mean, mu of p hat is going to be equal to p, which is the population proportion. And then sigma of p hat is equal to the square root of p hat q hat over n. So when you actually look at the margin of error formula, it's written as the z-score value, ZC, times sigma of p hat. If you look back at the margin of error formula for the mean in 6.1, we saw that the margin of error was ZC times sigma of x bar, right? So in each case, the margin of error is a z-score times a sigma value. So in that way, they're the same. It's just the way that we compute the sigma value for the population proportions is a little bit different than the way we did it for the means. This slide is just reiterating what I was saying about how the margin of error in 6.3 for population proportions mirrors what we saw in 6.1 when we were talking about the margin of error for the mean. And it all falls in line with the central limit theorem back when we first figured out what sigma of x bar was. This sigma of p hat behaves very similarly to that. So we want to look at an example now. And our example is this. We just want to find a margin of error. We're not putting this formula in context or anything. We just want to be able to see if we can use the margin of error formula. So let's see if we can find the error if we have an n value of 3600, a p hat of 0.64, and we want to build the 99% confidence interval. So we want to see if we can find the values for these conditions. So here's our solution. If C is 0.99, if we're looking at the 99% level of confidence, what would the z-score value be? So in your notes, there's a little cheat sheet table back in chapter 5. And if you look at that cheat sheet table, you'll see that the z-score associated with a confidence interval of 0.99 is 2.575. So that's the z-score we're going to use here. Then we want to look at p hat. In the formula, we need both p hat and q hat, but we have the relationship that says that q hat is equal to 1 minus p hat, so 1 minus 0.64 is 0.36. Now we have all the values we need to be able to find this margin of error. For our margin of error, we've got zc times the square root of p hat, q hat over n. The z-score is 2.575. P hat is 0.64, Q hat is 0.36, and the n value was 3600. When we multiply out just the square root part, it turns out to be 0.008. That's not a rounded value. That's actually the actual value of the square root. We multiply that to 2.575, and the margin of error is 0.0206. Here's another example, right? We want to see if we can find E if these conditions are present. So this time we're going to look at an n value of 900, still a p hat value of 0.64, and now we're doing a 90% confidence interval. Again, let's look at that confidence interval, 90%, 0.90. If you look back on that cheat sheet, the z-score for a 90% confidence interval was 1.645. So that's the z-score value. And of course, if the p hat is equal to 0.64, then the q hat is 1 minus that. 1 minus 0.64 is 0.36. So now we can plug it into our formula. We get zc, which is 1.645, times the square root of p hat q hat, so that's the square root of 0.64 times 0.36 over n, and the n in this problem was 900. If we simplify the square root, we get 0.016, multiplying that by 1.645. Our margin of error is 0.02632. All right, so now that we have gotten a handle on how to find the margin of error, we want to actually be able to develop the entire confidence interval. So we develop our process. So the first thing we're going to have to do in our process is find a point estimate for p, and we're going to call it p hat. Then there's a verification step. This didn't happen when we were finding confidence intervals for the mean, but we do have to do it here for the population proportions. So we verify the sampling distribution for p hat can be used by figuring out if n times p hat and n times q hat are both greater than or equal to 5. If they're not, you can't even do this process. So that verification process is very important to us. Then we're going to find the margin of error E, and we just got the formula for that, which said that the error is zc times the square root of p hat q hat over n. So then we can form our confidence interval in much the same way that we did with the mean. When we had the mean, we did the x bar value minus the error, x bar plus the error, because x bar was our point estimate. Well, with these population proportions, we're going to do the same thing, but now with p hat instead of x bar. So we're going to take p hat minus the error and p hat plus the error. And that's how we'll form our confidence interval. We have a little note here. The probability that P falls in the confidence interval is C. We saw that similar note when we were talking about the mean, where the probability that the actual population mean falls in the confidence interval was C. Now the probability that the actual population proportion falls into that confidence interval is given by C. So let's look at an example where we try to put this together in a more contextualized format. So we have a random sample of 10,000 Energizer 9-volt batteries. We choose that sample and the batteries are tested. Out of all the batteries, 130 of them are found to be defective. Create a 95% confidence interval for the proportion of all Energizer 9-volt batteries that are defective. Okay, so we need to kind of gather up our information to be able to find the margin of error. We need a value for P hat, we need a value for Q hat, we need to know the z-score value, and the size of the sample. So the size of the sample is 10,000. And to get our P hat value, we do x divided by n. So in this problem, the n was 10,000, the x was the 130 that were defective. So this is going to be 130 over 10,000, and as a decimal, that's 0.013. So that's our P hat value. Now we have to verify that the sampling distribution can be used. We have to take n times P hat and n times Q hat and make sure that both of them are greater than or equal to 5. We probably should figure out Q hat first. To figure out Q hat, that's 1 minus P hat, which would be 1 minus 0.013, which would make it 0.987. So n times P hat is 10,000 times 0.013, which is 130. And n times Q hat is 10,000 times 0.987, which is 9,870. Both of those are greater than or equal to 5. That's what the stars indicate on your slides, which means we can keep going, right? If they hadn't both been greater than or equal to 5, we would have had to stop. So now that we know that we can use it, we can go ahead and find our error. To find the error, we use the formula ZC times the square root of P hat, Q hat over N. For a confidence level of 95%, the z-score is 1.96. So we get 1.96 times the square root of 0.013 times 0.987 over 10,000, which if we use our handy-dandy calculadora, is 0.0022201,705. I'm going to go ahead and round this off to 5 decimal places, so it's approximately equal to 0.00222. So why did I go with 5 decimal places instead of 3 or 4, which we're kind of used to? And the reason for that is because this value for the margin of error is in proportion form. Oftentimes when we express these population proportion confidence intervals and margins of error, we convert them to percentages. Well, to convert a decimal into a percent, we're going to move the decimal 2 places to the right. If we move the decimal 3 spaces to the right, then that gives us our 3 decimal place accuracy that we're used to. So let's go ahead and form our confidence interval now by taking P hat minus the error and P hat plus the error. Remember that our P hat was 0.013. So if we take our P hat, which is 0.013, and we subtract 0.00222, we get 0.01078. If we add the 0.00222 to the 0.013, we get 0.01522. So in percentage form, we're 95% certain that the average percentage of defective 9-volt batteries in the population is between 1.078% and 1.522%. So there's that 3 decimal accuracy that I was just talking about. Alrighty, so we've got a little practice problem for you. A random sample of 800 first graders is chosen and tested for scoliosis. Out of all the children, 16 of them are found to have scoliosis. Create a 90% confidence interval for the population proportion of all first graders that have scoliosis. So go ahead and pause the video, give yourself a chance to work this out, and when you're all ready to go, press play. Okay, so first things first, we need our point estimate, our p hat, which is going to be x over n. So in this problem, the n is 800, and the x is the 16 children that were found to have scoliosis. So our p hat is 16 over 800, and 16 over 800 is 0.02. So if p hat is 0.02, q hat is 1 minus 0.02, which would be 0.98. Now we want to verify that we can continue to go through this problem by doing the n times p hat and the n times q hat. So when I do n times p hat, I'm going to get 800 times 0.02, which ends up being 16. Hopefully you realize, just from the formula above, that n times p hat will always equal x. If we look right here in the p hat equals x over n formula, if you think about multiplying both sides of this equation by n, this left-hand side would be n times p hat, and the n's would reduce away over here and just give us the x. So when we're trying to figure out n times p hat, it's just the numerator of that fraction. So we see that the n times p hat came out to be 16. N times q hat is going to be 800 times 0.98, and 800 times 0.98 is going to be 784. Now both of those are greater than or equal to 5, so we keep going. Next thing we need is to find the margin of error. The margin of error is given by ZC times the square root of p hat times q hat over n. So when we're looking at a 90% confidence interval, the z-score is 1.645. So we have 1.645 times the square root of 0.02 times 0.98 divided by 800, which as a decimal is 0.0081423346. Again, I'm going to go ahead and round off to 5 decimals here, and that's just 0.00814. So to form my confidence interval, I'm going to take the p hat value, which is 0.02, and subtract the error, and then the p hat value plus the error. So when I take the 0.02 minus 0.00814, I get 0.01186. And when I add the 0.00814 to the 0.02, I get 0.02814. So if I look at that in percentage form, I am 90% confident that the percentage of children with scoliosis in the population is between 1.186% and 2.814%. Now, if you remember when we were talking about the margin of error, we spent a little bit of time talking about minimum sample size. Well, we want to do that here too. And the reason that we want to do that, this population proportion confidence interval process is really what we see when we see polls, when we see percentages of people who support a candidate or are against a candidate or for some particular ballot measure or proposal. Those polls are given to us in percents. So the way that we form those percents is important. And if we want to have a particular margin of error, we need to know how to get the correct sample size to generate that margin of error. How did we do it when we were talking about the mean? We took the margin of error formula and we solved it for n. We're going to do a similar thing here. So this is our margin of error formula. If I'm trying to get the n by itself so that I can find the minimum sample size, the first thing I have to do is divide both sides by ZC. That way it's not on the same side with the n anymore. So that gives me E over ZC equals this square root, the square root of p hat, q hat over n. I need to eliminate the square root. To eliminate the square root from the problem, I square both sides of the equation. When I square both sides of the equation, I get E over ZC squared equals p hat, q hat over n. Square root's gone on the right-hand side. Well, there's a really interesting thing that you can do with fractions. When you have two fractions that are equal to each other, their reciprocals are equal to each other, as long as the fractions aren't equal to 0. So these fractions aren't 0. So if I take each fraction and flip it upside down, they're still equal. And that's what I've done here. That makes it easier to get the n by itself. Now to get the n by itself, I'm going to multiply both sides by p hat and q hat. The p hat and q hat reduce on the right-hand side, and they just leave the n. And the other side becomes p hat q hat times the fraction zc over e squared. And that's my minimum sample size formula. Alrighty, so let's formally introduce that. For the minimum sample size, for a confidence level C and a fixed margin of error E, the minimum sample size needed to estimate P is given by n equals p hat q hat times zc over e squared. There's an assumption going on here that you might not be aware of. We kind of had to do the problem first already, because where did the p hat and q hat values come from? Right? We didn't run into that problem when we were finding the minimum sample size for the margin of error, because it didn't rely on any values like that. It just relied on a standard deviation. But with this one, we have to know the values for p hat and q hat. So it assumes that we've already done this problem at least once, that we've already worked through it. What if we haven't? What if we have no information available to us at all? So if we don't have an initial value for p hat and q hat, then what we should do is set them so that we'll get the largest possible sample size. And that would come from p hat and q hat both equaling 0.5. In other words, if we don't have a percentage that p hat and q hat are, like if we haven't done the problem and found out that p hat is 37% and q hat is 63%, if we don't have any information like that, then we basically just say, okay, it's 50-50. 50% success, 50% failure. That will lead us to the largest possible sample size. If we do have information, we'll use that and that will shrink the sample size a bit. But if we don't, we say 50-50. So let's see that in practice. Last year, a travel agent conducted a survey to determine how many of her 850 clients were completely satisfied with their vacations. She found that 31% were completely satisfied. This year, she had 983 clients. She would like to conduct the survey again, but doesn't want to have to contact all of her clients. What is the minimum sample size necessary to estimate the proportion of her clients that are completely satisfied with a 95% confidence level and a margin of error of 4%. All right, so there's a lot to unpack right there. Let's go ahead and look through. First thing we know is we have some preliminary estimates. And the reason that we have preliminary estimates is because this travel agent had conducted this survey last year. So in the survey she did last year, she had 31% completely satisfied. That's going to be our preliminary estimate for p hat. If that's my p hat, then q hat must be 0.69. Because remember, p hat and q hat always have to add up to 1. So now what about the z-score? Well, for a 95% level of confidence, the z-score is 1.96. And the margin of error we want is 4%, so that's going to be 0.04. So let's go ahead and insert all this into the formula. N equals p hat q hat times the fraction zc over e squared. The p hat is 0.31. The q hat is 0.69. The zc is 1.96. And the error is 0.04. So when we multiply all this out with our handy-dandy calculators, we get 513.5719. We need to do some rounding. The reason that we need to do some rounding is because this is a minimum sample size. It can't be fractional. I can't contact a fractional number of people. So that means I need a whole number. And for minimum sample size, we saw with the mean, we always round up. That's true here as well. So we're going to round this up to 514. Now, traditional rules of rounding in this problem would have rounded it to 514 anyway. But even if this had been 513.2, we would have still rounded up to 514 so that we meet the minimum. So we put that in a note. When computing minimum sample size, always round up. Now we have a practice problem. A recent poll reported findings that 43% of Americans believe that the president is doing a good job. You wish to conduct a poll asking the same question. What is the minimum sample size necessary to estimate the proportion of Americans that believe the president is doing a good job with a 99% level of confidence and a margin of error of 2%? So go ahead and pause the video, work this out, and when you're ready to find out how it works, press play. Okay, so let's go ahead and look at our solution. We do have preliminary estimates because we had a recent poll that reported findings that 43% of Americans believe that the president is doing a good job. So that's our p hat. P hat is 0.43. If p hat is 0.43, q hat is 1 minus 0.43, which would be 0.57. Now we're looking at a confidence level of 0.99, 99%, and the z-score for that is 2.575. So now we can go ahead and shove everything into that formula. N equals p hat, q hat, times the fraction zc over e squared. The margin of error we're looking for here is 2%, so that would be 0.02 for e. So when we go and insert these values, we've got the 0.43 times 0.57 times 2.575 over 0.02 squared. Plug that into your calculator and make sure that you're doing that. Try these problems with the calculator and make sure you're entering it right. If you're having a problem entering this on your calculator, start with the fraction. Do the 2.575 divided by 0.02 and just press equals or enter on your calculator. Then square that answer and press equal again. Then multiply it by the 0.43 and the 0.57. And that should get you the right answer. And the right answer here is 4062.915469. But we remember our note that we just saw that says whenever we're computing minimum sample size, we always round up. So that would mean we would have to have 4,063 individuals in this poll. So if you ever look at polls on television or in a magazine, at the bottom they usually state the size of their sample. And it's always some weird number like 4,063. And if you've ever wondered why it's a number like that, it's because they've done this process. They started with a sample, they took that value and they went out and they did their polling. They figured out whatever margin of error it was. And if you just do it, let's say you decide to question 2,000 people. If you just go and question 2,000 people, you're going to get a margin of error that's, 3.714%. But what if they want just 3%? So they come back and they do this problem and they figure, okay, what do I need to do to make it 3% or to make it 2% for the margin of error? That'll tell them what their sample size should be. So they do it once, they find out a margin of error, and then if they want a particular margin of error, then they go back out and they sample more people to get to the correct sample size. And that brings us to an end of section 6.3. So please check on Pearson for your homework and have a great day.